Asteroids are small, rocky objects that orbit the Sun. They are remnants from the early formation of the solar system, providing a window into the conditions and processes that shaped our cosmic neighborhood approximately 4.6 billion years ago. Unlike planets, asteroids are much smaller and irregularly shaped, lacking the gravitational force to pull themselves into a spherical form. They are sometimes referred to as minor planets or planetoids due to their size and composition. Asteroids formed in the protoplanetary disk, a rotating disk of gas and dust surrounding the young sun. As the disk evolved, small particles began to stick together, forming larger clumps. These clumps, called planetesimals, collided and merged to create the planets. However, not all planetesimals coalesced into planets. In certain regions of the solar system, gravitational interactions and other factors prevented these smaller objects from accreting into larger bodies. This is how the asteroids we see today came to exist. The majority of asteroids are found in the asteroid belt, a region between Mars and Jupiter. The strong gravitational influence of Jupiter disrupted the planet-forming process in this area, leaving behind a vast collection of rocky debris. Other asteroids can be found scattered throughout the solar system, including near-Earth space and beyond. Asteroids vary widely in size, shape, and composition. They range from tiny fragments less than a meter across to massive objects hundreds of kilometers in diameter. The largest asteroid, OSIRIS, is about 940 kilometers, about 584 miles, wide and is classified as a dwarf planet. Asteroids can be categorized into three primary types based on their composition. C-type, carbonaceous asteroids, which are the most common type, making up about 75% of known asteroids. They are dark and contain a high percentage of carbon, along with other elements such as silicates. C-type asteroids are thought to be some of the oldest objects in the solar system. S-type, silicaceous asteroids are made primarily of silicate minerals and nickel iron. They are brighter than C-types and account for about 17% of known asteroids. M-type, metallic asteroids are composed largely of metallic iron and nickel, and they are relatively rare and often brighter than other types. Some asteroids also contain traces of water, organic molecules, and other materials that could provide clues about the origins of life on Earth. The asteroid belt is a vast region of space between the orbits of Mars and Jupiter, where most of the solar system's asteroids are found. This region contains millions of asteroids, though their total mass is less than that of Earth's moon. Despite popular depictions in science fiction, the asteroid belt is not densely packed. The average distance between asteroids is hundreds of thousands of kilometers. The gravitational influence of Jupiter played a significant role in shaping the asteroid belt. During the early solar system, Jupiter's strong gravity prevented the material in this region from coalescing into a planet. Instead, the frequent collisions between objects in the asteroid belt resulted in the fragmentation and scattering of material. Near-Earth asteroids are a subset of asteroids whose orbits bring them close to Earth's orbit. These objects are of particular interest and concern because of their potential to collide with Earth. NEAs are classified into several groups based on their orbital characteristics. Amor asteroids have orbits that approach Earth's orbit but do not cross it. Apollo asteroids have orbits that cross Earth's orbit, with semi-major axes larger than Earth's. Aden asteroids also cross Earth's orbit, but have semi-major axes smaller than Earth's. Atira asteroids, or interior Earth objects, have orbits entirely within Earth's orbit. Efforts to track and monitor NEAs are crucial for planetary defense. Organizations like NASA and the European Space Agency have dedicated programs to identify potentially hazardous asteroids and develop strategies to mitigate the risk of an impact. The exploration of asteroids has become a major focus of space missions due to their scientific and practical significance. Studying asteroids can provide insights into the solar system's history, the origins of water and organic materials on Earth, and the potential for resource utilization in space. Some notable asteroid exploration missions include NEAR Shoemaker, the first spacecraft to orbit and land on an asteroid, which studied the asteroid Eros; Hayabusa, the first mission to return a sample from an asteroid, Itakuwa; Dawn, which explored Vesta and Ceres, two of the largest objects in the asteroid belt. OSIRIS-REx, which collected samples from the asteroid Bennu and returned them to Earth. And Hayabusa 2, a follow-up mission that returned samples from the asteroid Ryugu. Future missions aim to explore more asteroids and even test technologies for deflecting potentially hazardous objects. Asteroids have played a significant role in Earth's history. Impacts from asteroids and other celestial objects have shaped the planet's surface and influenced its biological history. For example, the Chicxulub impact, caused by an asteroid about 10 kilometers in diameter, is widely believed to have triggered the mass extinction that wiped out the dinosaurs 66 million years ago. While large impacts are rare, smaller asteroids frequently enter Earth's atmosphere. Most of these objects burn up upon entry, creating meteors or shooting stars. Occasionally, larger objects survive their descent and reach the ground as meteorites, providing valuable scientific samples for study. Asteroids are rich in valuable materials, including metals like iron, nickel, and platinum group elements. Some also contain water, which can be used to support human space exploration by providing drinking water, oxygen, and hydrogen for fuel. The concept of asteroid mining has gained interest in recent years, with private companies and space agencies exploring the feasibility of extracting resources from these celestial bodies. The potential for asteroid mining has far-reaching implications for the future of space exploration and industry. By utilizing resources from asteroids, humanity could reduce the cost of space missions and establish a sustainable presence in space. Asteroids have captured the imagination of writers, filmmakers, and artists for decades. From thrilling disaster movies like Armageddon to scientific documentaries, asteroids are often portrayed as both threats and opportunities. While Hollywood depictions often exaggerate the dangers of asteroid impacts, they have helped raise public awareness about these fascinating objects. Asteroids are more than just rocky remnants of the solar system's past. They are keys to understanding our origins, potential resources for future exploration, and a reminder of the dynamic and ever-changing nature of our cosmic environment. As our knowledge of asteroids grows through observation and exploration, so too does our appreciation for their role in the story of the solar system and their importance to humanity's future in space.